You know that feeling when you're just staring at your screen, completely frustrated by inflexible code? I mean, we've all been there, right? If you've ever felt like your software projects inevitably turn into these tangled, messy webs that are just impossible to update, well, you are definitely not alone. But the good news is, there's actually a structural cure for all this chaos, and you're in exactly the right place to find it.
Welcome to today's explainer. We are going to be completely demystifying object-oriented programming design patterns. Now, we're basing our journey directly on the IBDP computer science syllabus, but honestly, whether you're studying for a big exam or you're just trying to write cleaner, more professional code, these concepts are absolutely going to transform how you view software architecture.
Okay, let's dive right into this. Here is our roadmap for today. First, we'll decode what design patterns actually are. Then, we'll break down the singleton, factory, and observer patterns. After that, we'll practice matching those patterns to real-world problems, and finally, we'll clear up a few common misconceptions.
All right, starting with Section 1, Decoding Design Patterns.
So, what exactly are they? Well, right off the bat, a design pattern is definitely not just a finished chunk of code you can copy and paste into your project. Actually, it's more like a blueprint. It's a general template, a highly reusable idea that helps programmers solve a common, recurring software design problem. Think of them as describing a proven structure for your classes and objects. And the best part, they instantly improve communication across a team because developers can just name a known solution, like a shorthand, instead of having to explain some massive complex structure from scratch.
Developing this kind of pattern mindset is incredibly powerful. It works a bit like this. First, you notice a familiar design issue that just keeps popping up. Once you spot it, you select a known, proven pattern to solve it. And because you used a standard, recognizable structure, your code instantly makes sense to the rest of your team. That means extending and debugging the program becomes an absolute breeze, drastically improving your maintenance over the long haul.
To summarize this into the crucial exam-style takeaways, the real reasons why programmers actually use these blueprints in the wild, it boils down to 4 huge benefits. First, consistency. Teams are applying the exact same proven structure. Second, flexibility. Your code can adapt and change without needing a total rewrite from the ground up. Third, reusability. Your classes can actually work across multiple different projects. And fourth, maintainability, making your program so much easier to test, understand, and extend later on.
Let's move on to Section 2, the singleton, one shared instance.
So, you're going to want to use a singleton when exactly one shared instance of a class should exist in the entire program. A few classic examples of this would be an application settings manager, a printer spooler, or a game score manager. The crucial thing to understand here is how the class restricts object creation. The constructor is tightly controlled so that every single request from anywhere in the program returns the exact same shared instance. It's kind of like a shared settings object in your favorite music app. You definitely do not want conflicting copies of your preferences floating around.
But, every pattern has a cost. It's a balancing act. On the plus side, a singleton prevents the accidental creation of multiple copies, makes shared configuration super easy to access, and it saves on memory. On the flip side, though, it creates this global-style access that can make testing an absolute nightmare. It can silently hide your dependencies, and if you overuse it, your programs become tightly coupled and way less flexible. So always remember, use a singleton only when it is absolutely essential, not just because it feels convenient at the time.
All right, Section 3, the factory pattern, centralized object creation.
You'll want to pull out the factory pattern when object creation really needs to be centralized, or when the exact class you need to create might vary based on a specific situation. For instance, picture an ordering system that needs to spit out a bike, a van, or a drone delivery object depending on the details of the order. Instead of calling constructors directly all over your code, the factory just handles it for you. This brilliantly hides all those messy construction details, which is absolutely perfect for dynamic scenarios, like, say, spawning different types of enemy objects in a video game depending on the current difficulty level.
The workflow here is just incredibly efficient. Let's walk through it. First, an input or a request comes in. Then, the factory logic evaluates it behind the scenes to decide exactly which subclass fits best. Finally, the factory hands that correctly constructed object right back to the program. It basically takes all that complex creation logic and centralizes it into one tidy, manageable place.
Moving to Section 4, the observer pattern, automatic state updates.
The golden rule here is super simple. Use the observer pattern when one object changes its state and other connected objects need to be informed automatically. In this setup, you've got one central object, we call that the subject or the publisher, and then you have multiple other objects known as observers or subscribers. When that single subject changes, it immediately pings all of its registered observers so they can automatically update themselves.
Honestly, you see this literally everywhere in the real world. Typical uses include GUI event handling, news or live weather updates, stock price alerts, and in-game achievements. It elegantly solves a really classic problem. Imagine a local weather station. When the temperature data changes at the source, the subject, you might have a smartphone app, a website, and a digital wall clock that all need to update immediately to stay perfectly in sync. The observer pattern handles that entire communication flow beautifully.
Okay, Section 5, Matching Patterns to Problems. Choosing the right tool for the job.
Now, what's really interesting about this side-by-side comparison is the main cautions for each pattern. A singleton ensures exactly one shared instance, sure, but it behaves like a global object, which seriously reduces flexibility. The factory pattern creates objects without exposing the messy details, but adding that extra layer of abstraction can be totally unnecessary overkill for really small apps. And the observer is great for notifying many objects of one change, but having way too many observers can make your program's flow incredibly hard to trace. You really have to keep these trade-offs in mind.
So let's put this into practice and see if we can apply it. Imagine a school app that has one timetable manager, and this manager absolutely must be shared by all the different screens in the application. Based on what we've just covered, which pattern do you think fits this problem best? Just think about it for a second.
If you guessed singleton, you hit the nail right on the head. Why? Because we actively need to enforce one single shared timetable manager to avoid creating weird, conflicting copies across different screens of the app. It's literally the perfect fit for managing a single shared resource.
Let's try just one more quick challenge. A scoreboard, a timer display, and a sound alert all must react immediately when the central game state changes. Out of the three patterns we talked about, which one is the right tool for this kind of dynamic update problem?
Boom! It's the observer pattern. And the reason why is that you have several dependent output objects, the scoreboard, the timer, the sound, and they all need to automatically respond to one changing subject, which in this case is the game state itself. It's the perfect demonstration of that subject to multiple observers flow.
And finally, Section 6, Misconceptions and Key Takeaways.
Let's clear up a few myths right now. First off, a design pattern is a reusable structural idea. It is absolutely not a full copy-paste program. Also, and this is a big one, throwing more patterns into your project does not automatically equal better code. Actually, if you force them where they aren't needed, they just add bloated complexity. And remember, you don't need a factory for every single object in your system, only when the creation logic actually varies or genuinely needs to be hidden. True programming expertise means knowing exactly when a pattern is actually required.
As we wrap up this explainer, I want to leave you with this to really chew on. Why should patterns be chosen carefully to solve a specific problem, rather than just being added automatically to your code as some sort of checklist? Think about the trade-offs we discussed, the cautions, and the true underlying purpose of software architecture. Writing professional software isn't just about typing code, it's deeply strategic and thoughtful. Thanks so much for joining me on this deep dive into design patterns, and I will catch you in the next explainer.